So in some sense, this should be a decent approximation. And the idea of WKB is to take that seriously. So So the actual WKB method is not just this, but it's to search for solutions where this is sort of the leading behavior. So let me call this solution psi I WKB, the solution that I'll search for, should be the exponential of, just as before, 1 over zeta times the integral of lambda I. But now it won't be exactly that, it will be multiplied by something. But that something we say should be regular as zeta goes to 0. So this EI now is not just the elementary basis vector, it's some generic thing which depends on zeta in some generic way. And the idea is if you just make this sort of formal ansatz for a solution, so using this ansatz, you can sort of recursively determine the higher, you can recursively determine EI as a power series in zeta. EI zeta as a power series in zeta. Okay. So suppose that works. Suppose for a second that literally worked and produced actual solutions. Then you would have effectively abelianized your connection because you've sort of decomposed it. You've given k canonical flat sections, so you decompose the thing into k lines. The normalization, I wouldn't say exactly it's k honest sections because this integral, I haven't specified the lower limit for this integral, so there's some ambiguity certainly in the overall normalization, but at least you've succeeded in decomposing the thing into k lines. Right? So if psi WQ, why am I saying if they really existed? The point is, they do really exist, but they exist only as formal power series in zeta. They don't exist as actual analytic solutions. So this power series tends not to converge. But suppose for a second that it did converge, or suppose that you work sort of formally in a formal neighborhood of zeta equals 0, then what would you get? So if they really existed as honest functions of zeta, then they would naturally abelianize nabla. But to be precise, they don't abelianize it to a they don't abelianize it into a connection on C because these lambda I are the eigenvalues and they're naturally branched over the they're not single-valued functions on the curve. They naturally live on the cover. So precisely what I mean by abelianize is that they realize it as the push forward they realize it as the push forward of a GL1 connection over the covering. Oh, well here's as the push forward of a GL1 connection, nabla abelian over the spectral curve sigma, which is now, so before I was defining it in terms of some differentials, now I'm defining it a priori slightly different way. I've got some matrix value 1 form phi, and the spectral curve now is literally a spectral curve. It's the determinant, you know, it's given by the characteristic polynomial of. It's just the covering by the eigenvalues of this matrix phi. So WKB does provide a kind of formal abelianization. On the other hand, we know this abelianization can't be actual, right? Because we emphasized before that you can't really realize the thing is the push forward of a GL1 connection upstairs. The monodermy would be wrong. And that's exactly related to this fact that these WKB solutions are only formal solutions. They're only formal power series in zeta. So we only get nabla absolute formally around z equals 0. Okay. So now on the other hand, in the story of these S-wall networks, I was talking about a kind of actual abelianization, right? It was an actual map from flat connections on C to flat connections on abelian connections on sigma. And so you could ask, what's the relation between that? You know, is there any relation between that and this kind of formal abelianization that's provided by WKB? And what I want to say is that there is a relation. The two procedures are sort of naturally compatible. So, roughly speaking, what's going to happen is that this actual abelianization that I described is going to give some flat sections whose asymptotic expansion is exactly the asymptotic expansion of these psi I WKBs. So how does it work? So I want to compare WKB abelianization now with the actual abelianization provided by the S-wall network. Well, okay, so suppose as above, that nabla is phi over zeta plus d of zeta. So I'm going to apply our actual abelianization procedure to this particular family of connections. But our procedure, of course, depended on some extra stuff, right? It depended on a choice of theta, it depended on a choice of these differentials. So now here, those choices are kind of provided to me. So I'll take, we'll build the S-wall network using the differentials. Using phi, I just want them to be exactly the coefficients of this characteristic polynomial. So I want the spectral curve to be the same spectral curve. So in other words, the determinant of this phi was a matrix. Yeah, notation so this phi was the matrix that appeared here, and this phi is the tuple of differentials that are associated to it. So the determinant of phi minus lambda I should be just equal to the other equation that I wrote, lambda to k minus sum from I equals 2 to k of lambda to the I, lambda to the k minus I, phi I equals 0. So this, given this phi, this determines now these differentials. They're just traces of power to the phi, more or less. So that gives me some definite tuple of differentials here. And then I also have to fix the phase theta that entered the construction, and the theta that I take should be just the argument of zeta. So then, okay, so having done this, now I can apply this abelianization procedure. So what I say now, I think, is a theorem for k equals 2, and it's a conjecture for k greater than 2. So apply abelianization. So this family nabla of zeta goes over to a family nabla ab of zeta connections on. This was a connection on C. These are abelian connections on sigma. And so now you ask, what are the relations? Well, in particular, once you've abelianized the thing, concretely, what does that mean? Well, if you look at how the procedure actually worked, this provides you in particular with a decomposition of this rank 2 bundle here into 2 lines on the complement of the S-walls. So on each region in the complement of the S-walls, I'll get a pair of flat sections, and they're going to jump as I move from one region to another. So this provides, in particular, sorry, did I say 2 flat sections? In k equals 2, it's 2 flat sections. In general, it's k flat sections. So in particular, flat sections psi I actual now, so I'm not writing WKB. Psi I of zeta, from I going from 1 to k, on the complement of the S-walls. So Zenabla flat sections and they jump in some specific way when you go from one region to another. Let me cross it this way. So they're not like, they're not global flat sections or anything like that. They're just flat sections in each little domain. So concretely, let me be a little concrete about what these things are. So in the case k equals 2, you can say exactly what they are, and they're not anything very complicated. So again, for this explicit description now, I've used Spock and Goncharov's results that sort of give you an explicit picture of what this abelianization is. So for k equals 2, this is something concrete. So here I have the my S-wall network, something fairly simple. I need the blue. So the picture is we've got this curve, it has some punctures on it. We've got S-walls that kind of flow down to the punctures, and so the region is divided into some domains. So in each domain, I can ask what will be my basis. So here I'm supposed to produce for you 2 flat sections. There's supposed to be 2 canonical flat sections in this region, and what they are. So same at this point here. So psi I in this domain. From this domain, I've got. So this domain has 2 punctures on it. It's like a little diamond, right? So there's 2 punctures. So let me call these punctures Z1 and Z2. And at each of these punctures, if you look at the behavior of the local system around each of these punctures, it just has, well, at least, again, I just look at the most generic thing. So generically, it has some GL2 valued monodromy. So it has just 2 distinct monodromy eigenvalues. So you can look at those 2 eigensections. Those are some distinguished sections. Now, I want to get rid of even that little Z2 choice. I want to pick a definite one. And the one that I pick So psi I is the monodromy eigensection at Zi, which, so if you analyze the behavior of the equation along one of these trajectories, any one, so it could even be one of the generic trajectories. If you analyze the behavior of the equation along any trajectory, what you'll find is that one of these monodromy eigensections is exponentially growing and the other one is exponentially decaying. And the monodromy eigensection that I want is the one which is exponentially decaying. As z goes to zi. So psi I, so I look at one of these monodromy eigensections as a function of z. As I go into the singularity, it either decays or explodes, and I want the one that decays. This sort of, it's called the, I think the WKB people call it the recessive solution. So that gives me some distinguished basis of two flat sections here, two flat sections here, and so on. But they're not the same. They differ from each other by some, by some simple 2x2 matrices when you go from one region to another. So take those. So in this case, we take those two small flat sections. But in general, you would similarly get some basis of k flat sections. And the statement. So now the statement, which is a theorem for k equals 2, is a conjecture in general. So the statement is that if you look at those particular flat sections, and you look at them in the limit as zeta goes to 0, so claim, conjecture, but it's a theorem for k equals 2. So the flat sections psi I, considered as functions of zeta. If you look at their, so they're discontinuous, but if you look at their asymptotics as zeta goes to 0,
so do you fix the argument of zeta?
Yes, definitely, because right, the whole construction of the thing depends on the argument of zeta, right? Depends on theta. So the thing will definitely jump as I change the argument of zeta, and that's crucial. The thing couldn't have had this asymptotic globally. It couldn't have been continuous and have this asymptotic globally. But the way I choose to say it actually is that this psi I of zeta, right? It was defined in a way which depends on. It was defined in a way which depends on zeta, but that's fine. So then I've defined it in a univalent way. It happens to be discontinuous. It's discontinuous as a function of zeta, but its asymptotics are not discontinuous as a function of zeta. So somehow the jump when I cross from here to here is by a section which is decaying much faster than the original one. So the asymptotics are not affected by these jumps. And so what I want to say is that psi I of zeta goes like psi I WKB of zeta as zeta goes to 0. So it's sort of this, it's a sense in which these formal asymptotics can become something real. It's not a converging series. The WKB series is absolutely not converging, but nevertheless there can be a function that has those asymptotics. Now typically what happens in that situation and what happens here is that those asymptotics are only valid in some, they're not valid, there's no continuous object that has those asymptotics, but rather the situation is like this. So as zeta goes to 0, you have these so-called Stokes rays. So what you can do is you can make a solution, you can make an object which has globally the correct asymptotics, but which has some discontinuities at those Stokes rays. And here the way the Stokes rays are appearing is if I sit at some point and I vary the parameter zeta, right? If I vary the argument of zeta here, then one of these S walls will come and hit me, and at that moment my basis of sections will jump. So this turns out to be quite a useful thing. Yeah, and maybe Okay, maybe this is a good moment to take a break, and then I'll explain one of the uses of this.